We have a relatively short session. I think we come to the last paper for the session. Paper title is under frequency load shedding based on dynamic system information, and the authors are Perera and RVDHN Rajapaksha. The presenter is Mr. Rajapaksha, Ms. Rajapaksha. Ms. RVDHN Rajapaksha is an electrical engineer at the Ceylon Electricity Board, currently working as a maintenance planning engineer in Transmission Asset Management Division. She is graduated from University of Moratuwa and obtained her MSc in electrical engineering from the same university. Prior to joining CEB, she was a design engineer at the Central Engineering Consultancy Bureau. May I ask Ms. RVDHN Rajapaksha to start the presentation?
Good morning, everyone. I'm Hansi Rajapaksha. I'm an electrical engineer from Ceylon Electricity Board. I'm here to present the research paper titled Under Frequency Load Shedding Based on Dynamic System Information. The authors are Professor Perera, who is a senior lecturer in Department of Electrical Engineering, University of Moratuwa, and myself, Hansi Rajapaksha. This is the outline of the presentation. First, I'm going to elaborate on the weaknesses of the present load shedding mechanism, and then about historical failures we have analyzed. The proposed load shedding mechanism under frequency load shedding based on dynamic system information, and introduction, MATLAB simulations, PSA simulation, result analysis, finally the conclusion. If we consider what are the basic requirements for a load shedding, first one, we can say to prevent the collapse of the power system and also to maintain system frequency and system voltage within permissible range, and also to keep the remaining portion of the system operational after disturbance. What are the weaknesses of the present load shedding mechanism? First, we have analyzed each and every weakness. First one, we can say there can be a possibility for a system collapse due to inadequate load shedding. And also there can be a possibility for excessive load shedding, as these load shedding tables are predefined. More feeders can get interrupted than the required quantity. And also in our present load shedding mechanism used by CEB, reactive power produced at each feeder is not under consideration. Same predefined load shedding table is used for off-peak, day peak, and also for night peak. So best solution is to go for intelligent load shedding mechanism. First, we have analyzed some historical failures. First failure, I'm going to elaborate on one failure. That is a partial failure occurred on 6 May 2013. This failure has initiated due to an earth fault occurred in one of the circuits in 132 Sapugaskanda Kalaniya line. Anyhow, distance protection at Sapugaskanda end was worked, but isolation at Kalaniya end did not work. Therefore, backup protection was initiated at line 2. But after that, Barge power plant was tripped, and one after the other, 6 power stations were tripped. Therefore, due to the decrease in frequency, under frequency load shedding was operated up to load shedding stage 4. When we analyze what is the loss of generation and what is the load shutdown under load shedding, we can see there's a huge gap between two amounts. The loss of generation was about 203 megawatt, while the load shutdown under load shedding was about 296. We can say excessive loads were disconnected under UFLS. And also, as reactive power at each feeder is not under consideration, we can see several voltage sags and swells. These are the voltage sags observed in Kotugoda Gistap station, and also we can see voltage sags at Norachole power station regarding this failure. Through analyzing some other failures, we also observed that some loads were unnecessarily interrupted through under-frequency load shedding. As you can see in these graphs, under load shedding stage 1, 2, 3, you can see there are some loads even below than 2 megawatt were interrupted. So better solution is to go for under-frequency load shedding based on dynamic system information. The basic objective is to develop an algorithm to make an optimum and also an reliable load shedding activity through updating load shedding tables, which must be based on actual consumption data of the feeders. So we can say this is an intelligent load shedding application. This is the introduction to intelligent load shedding system. System data is always monitored through advanced real-time power system monitoring and simulation system. Data collection server is located at control center. Here the data such as generation details, demand data are also getting updated with the time. ILS server is also located at the control center where load shedding tables are getting updated on the current values. These updated load shedding tables are getting uploaded to the PLCs located at the load circuit breakers. Whenever system variation in system frequency of dF by dt frequency variation rate occurred, it will sense by the PLC, and PLC will send signals to relevant load circuit breakers to shed the load. First, we selected the reduced network from CEB network to perform MATLAB simulations. This is the reduced network we used. Here we uploaded on-site generation and demand of each dispatch station, and also we considered loads that can be shed separately, and we imported those data to MATLAB software. Then we designed graphical user interface in MATLAB so that user can perform machine shutdowns and observe what is the frequency behavior and what are the loads that can be shed. But the problem was we can't do comparison of both methods in MATLAB, the present method and the method we are proposing. Therefore, we also did the simulation in PSSC, Power System Simulator in Engineering, used by Ceylon Institute Board and most of the power utilities in the world for the power system simulation. This is the network we used in PSSC. We did the result analysis basically in 3 areas. First, by analyzing frequency and voltage plots obtained through PSSC, and also by analyzing difference between total loss of generation and total disconnected load under load shedding. In addition to that, by comparing megawatt of each disconnected load for any high variation. This is how we did the PSSC simulation, as the diary file written for under-frequency load shedding in PSSC does not contain load data feeder wise. So we had to input active power and reactive power for a particular date for each feeder, and also generation data was also collected and entered into PSSC. After that, we modeled the PSSC file according to our data, and we considered 3 scenarios. First one is trip-in of both machines in Nivalakshapana and Sammanalavawa, and the second one is both machines in Nivalakshapana, Sammanalavawa and in Old Lakshapana, and third one in the real actually happened failure, that's trip-in of machine in Norachola power station. Then we did the PSSC simulation using diary file we have written for ILS for each scenario, and we did the same simulation for the same 3 scenarios using existing load shedding mechanism under frequency load shedding using already written diary file. First analysis we did by comparing the frequency and voltage waveforms obtained in PSSC. As you can see, under ILS, frequency has got stabilized earlier than in UFLS, and also under existing load shedding mechanism up to load shedding stage 2 got were operated, because after that only the frequency has got stabilized. If we consider the voltage waveforms, we can see under ILS voltage has got stabilized earlier than in UFLS, and also you can see many voltage overshoots under existing load shedding mechanism UFLS. If we consider for the case study 2, situation was the same. Even up to load shedding stage 3, under frequency load shedding was operated under existing load shedding mechanism, and also frequency has got stabilized earlier under ILS in case study 2 also. If we consider the voltage waveforms, situation is like earlier, where we can see many voltage overshoots under UFLS. Case study 2, you can see up to load shedding stage 3, that is the tripping of machine 1 in Norachole power station. Under UFLS, up to load shedding stage 3, under frequency load shedding was operated, but under ILS, frequency has got stabilized earlier. Considering the voltage waveforms, the situation is the same. You can see many voltage overshoots under UFLS, but under ILS, that is not the case. So we also did the result analysis depending on the load shed through ILS and UFLS. You can see that many feeders got interrupted under UFLS than in ILS, and also the percentage of uninterrupted load is very much higher. Third analysis we did by comparing the megawatt of each disconnected load. You can see under UFLS, some loads were unnecessarily interrupted because it hasn't got aware about the real load of that feeder. But under ILS, all the loads disconnected were falling in the same region. Situation is same for the case study 2. Under UFLS, unnecessary loads were interrupted, but under ILS, all loads were falling in the same region. As a conclusion, I can say that through application of under-frequency load shedding based on dynamic system information to the CEB network, there are several benefits can be achieved. Probability for a total failure is reduced, and also number of feeders interrupted is reduced. Further to that, quantity of real power curtail is reduced, and also, as you have seen in the voltage waveforms, voltage profile during contingency period is improved. This requires further studies. And also, this has a large contribution to reliability indicators such as SID and SIFI. Thank you.
Thank you very much. Shall we first give a hand to the presenter?